Optimize. A journey through database query optimization. This course is filmed on location at Carnegie Mellon University in front of a live studio audience.
This was, like I said, we're picking up where we left off last class. I'm talking about like the first query optimizer from IBM, and then now we're going to get into the second one from IBM, for Starburst. And again, you start to see how the sophistication, the complexity of these optimizers is increasing. We're jumping 10 years ahead into the 1980s, still before most of you were born, but the optimizers are starting to do a lot more things. Before we get to that, though, I do want to go over some mistakes that have come up that people emailed about. So the first one, the mistake I made last class was that I said Charles Bachman was like the third or fourth, the second or third person that won the Turing Award. That's incorrect. He's actually the eighth person. So the Turing Award started in 1966, and so Bachman won in 73. So he was the eighth person. Does anybody know who the first person who won the Turing Award was? Perlis. Where's Perlis from? CMU. He did his undergrad here, and then he did his PhD, I think, at MIT, and then came back as faculty, and he won the first Turing Award in 76 or 66. All right, and then the other thing was that a German emailed me and was correctly pointed out that my definition of the complexity of the number of join orders you could possibly have was off. I just said it was a catalog number, but it's really where n you have n tables you want to join in a single query. If you're just doing binary joins, then it's n minus 1 factorial, and then this catalog number is another factorial that's really big as well. So it's the multiplying these two together gets you the total number of possible join orders you could have. Again, just doing binary joins or dyadic joins. It's still a huge number, right? And so it's not feasible for us to actually consider all possible join orderings. Right, and again, if I make any mistakes, send this email. And you don't send weird things. People started sending weird things, and that's not good. Okay. All right, as I said, last class, we talked about System R, and we said it was the first cost-based query optimizer, and that how it was using dynamic programming to choose the optimal join ordering for queries, right? And that optimal ordering was estimated through a cost model that was derived from statistics that were generated from examining the tables, right? The key thing to point out, and what we're going to see different in Starburst today and in going forward in other query optimizer implementations, is that System R, because it was sort of the first one and it was running on primitive hardware, certainly even to the 1980s, relative to the 1980s, it was very primitive. But the one of the big things they did to simplify the problem was they would first select the access method they were going to use for a table, and then they try to figure out the join order. But as you know, again, from the intro class, oftentimes the join order will be, what is the best join order to use is going to be influenced on what the access method actually is, right? If you have an index on a table, if you pick a sequential scan, then you may not be able to use that index to do like a nested loop join, right? Or if you want to do a sort merge join, if you don't select the table in a sorted order, then you can't use the merge join operator, right? So what the Starburst paper will point out, and what we'll see in future optimizers, is that the better thing to do is the right thing to do is that you want to select the access method at the same time you're actually selecting the join method, right? And so that'll sort of set up how we're going to do more complex things, looking at all the rules that are in Starburst today. All right, so let's go back in time and talk about what was going on in sort of the world of databases in the late 1980s, mid 1980s, that set us up to why there needed to be something like Starburst. So there was two big trends in the late 1980s. One was object-oriented databases, and the other one was called active databases. So object-oriented databases are basically a database where the data model that I think they're actually storing is like an object, like in Java, Python, C++, whatever you want, right? And the idea was that you're writing your application in object-oriented code, because that was the hot thing, right? Smalltalk came out, that was a hot thing. C++ was a little bit later, right? Like object-oriented was sort of the big fad at the time. And the idea was, instead of having a relational database that organized everything as tables and relations, you want something that stores your program data natively. So you just take your application code where you're writing against objects, and then just have like a save function that then sucks that out and puts that directly into the data system in that native form. So now when you go bring that state back into the application code, it's not doing a bunch of joins across a bunch of different tables, just going, grabbing that single object, right? So there was a bunch of database systems built at this time, and part of it was because there was new applications coming along that didn't look like the traditional business applications of relational databases from the late 1970s, early 1980s, or even the 1970s entirely, right? Things weren't always in a tabular form. The other trend, less well known as object-oriented databases, were these things called active databases. The basic idea there was the database was going to be this living being that could react to changes in either internally in its own data set or outside things that would occur. And it could update and modify its own contents automatically. It's basically just triggers, right? If you want like if someone updates this table, you'd fire a trigger that then to do something based on that event, right? But again, triggers are super common now. In the 1980s, that was a new idea. And then we'll see in a second why this is sort of related to Starburst, because they're at least in the initial version of the query optimizer, they're going to put everything in the database system, and sort of almost it's the same way you would use the same rules to do query optimization. You could then use them for doing triggers on data and so forth. But the one we care about the most is this object-oriented databases, right? This was considered a real threat to relational databases because the relational model sort of said like you have these scalar types in these tables. You can't have arrays. You can't have nested objects in your data. And then if anybody came along and said, I have this new data type that isn't in the SQL standard or isn't in your relational database, you'd have to go rewrite the entire thing. Whereas people wanted to be able to write all these complex types in application code and have the data system store that natively. So people recognized that you wanted to be able to easily extend your database system to support new applications, new things, and to make them sort of more competitive with these object-oriented databases. This is why technically Postgres, these in Stoneberger's original papers, they're not called a relational database system. They're an object relational database system. It just means that it's the relational model that can have extensible types and operators and other things. So around the sort of same time here, going back now for query optimizers, we talked about this sort of history here. Now we're entering this phase here where after we sort of built the first ones in System R, in Ingress and other early ones, people recognize that, okay, I want to have an extensible data system. Before object relation was considered a term, like people knew they wanted to be able to extend their database system without having to rewrite the entire thing, right? I always give this one example that Sternberger always brings up. Like part of the motivation of making Postgres be extensible was when they were selling Ingress, Ingress had a built-in data type, date type, and it was based on the Gregorian calendar, the calendar we use. But then when they try to sell the database system to all the banks are like, great, we need a date type to compute interest, but we run on the Julian calendar, which is the number of days since Julius Caesar was either killed or born, one of the two, right? Because that's how they would compute interest, because you'd always have 30-day months. And so since in order to add that new date type to the database system, they had to go make a bunch of changes to the system. And so Postgres, the idea was you'd have this core relational database system that had this base functionality you'd expect with certain data types, operators, and functions. But then if someone wanted to add new functionality to it, like a Julian calendar date type, they could implement against an API and link that in without having to rewrite the entire thing, right? And so as part of that, people recognize, okay, well, it's not just having these, a new date type or new operators to process them. You also, the query optimizer needs to be somehow aware of what these things you're adding to it are, so that it can choose the optimal plan. So as part of that, that's what sort of fed into these movements where people wanted a way to easily add new things to a query optimizer without having to rewrite everything from scratch. And so these two sort of trends are categorized as what we'll call optimizer generators. And so the idea of an optimizer generator is that instead of having everything that you could possibly do in your data system baked into the optimizer itself, that you would have this sort of separate framework where you could define what the optimizer should be do under different conditions and on different kind of operators and different data types. And then you would have a way to then either compile or inject that optimization rules you've constructed into your database system without having to rewrite everything. So the Starburst paper, kind of, at least the paper I had you guys read, doesn't really talk about it in terms of being an operator or optimizer generator. The Volcano paper you'll read next class, and certainly Cascades after that, this is definitely more heavily biased to being an optimizer generator. But the high level idea is still the same, that you want to be able to have people add new things to your optimizer or to your database system and have the optimizer be aware of these things without having to rewrite everything, right? And so a big thing that we're going to see in Starburst today and in the optimizers next week is basically how they're going to define how they will have these patterns to match certain characteristics or aspects of a query plan, and then the transformation or change or modification you would then want to make to it, right? And the idea is that you could do all these transformations and this pattern matching separate from how you're actually going to do the search to find an optimal query plan, right? That someone could just define, if I see this, then make this change, and I don't care how you're actually going to go ahead and execute that. Is that clear? So the optimizer generator is considered the right way to build these things, and we'll see more examples of that as we go along. Right? In the case of System R was like everything that all the logic was hard coded in. I don't think it was written in C. It was assembly, but all the logic to do all the transformations and the search and all that was intertwined in a single code base. Whereas if you go with this approach, you could have one team build all the optimization rules, and another team is focusing on the engine the search engine to go ahead and apply them. So related to, again, the breakup between the unified search and the stratified search, right? Basically the two different approaches you could build for an optimizer is going to be how you're going to consider what rules to apply when you're doing query optimization. And so the stratified search we'll see today in Starburst, the idea is that the query optimization is going to be done in multiple stages, where some transformations will occur in the very beginning, and those you actually don't need a cost model, right? You just kind of check and see, does the query plan look like this? If yes, I know I can go ahead and make this change. And then the other approach is going to be from a unified approach from Volcano and Cascades, where you're kind of throwing all the transformations and everything you could do all in the mix all together, and then you just let the search engine try to figure that out. Roughly also means, are you doing top down versus bottom up, but not entirely, right? And as I said, I think in the first class, the lines between these are very, very, very blurry, right? You'll see Starburst today, they're going to have an explicit first stage doing the rewriting, and then they do the cost-based search. In the unified search, at least in Cascades, in the very beginning, they talk about, oh, it's going to be one single search, no separate stages, all at once. You're trying to figure things out. But in case of SQL Server, the paper talks about they do things in stages where they say, I only want to do these transformations. If it's an easy query, do these first set of transformations. If I think I need to do more, then here's another sort of set of transformations I can do. Yes?
I think approach is also a big kind of use cascades. So it's like
it's Cascades, but they have a separate rewrite stage. Yeah. All right, so this is just repeating what I just said. If I can't click, all right. The stratified search, again, the idea is that there are going to be a bunch of rules that we can do rewriting on the logical query plan, where we only need to check whether the rule should be applied. And if the rules are implemented correctly, assuming that they are, of course, there's always be bugs, but that's independent of what we're talking about today, that if the rule is allowed to be applied, then the outcome will be a valid plan. So if you start with a valid query plan, some rule gets fired based on some condition, the output after that transformation will still be still be valid. And the idea here is that you want to sort of nudge the query plan in a direction that's more amenable for the cost-based search. Again, we'll see this again in Starburst today, but the idea for them was sometimes queries show up and they're written in such a way, like the SQL query itself is written in such a way that the optimizer can't easily figure out, here's a bunch of different alternative plans I could choose to execute it. Nested queries is going to be the big problem that they try to overcome, right? So like if you don't unnest a nested query, then it's almost like this procedural query plan. Like here's this, you got to run the nested query first, then you run the outer query. Whereas if you can unnest it, replace it as a join, then now you can start doing all your joint enumerations and try different orderings of things to try to find the best plan. But the key thing is that in the initial stage here, we don't need a cost model. We know it's all about on the logic. Does the rule match? If yes, go ahead and apply it. And then unified search, again, I don't want to say too much because we'll talk about this all next week, but the idea is that you have all your transformation rules. Some of them could be cost-based, some of them may not be cost-based. But you're just throwing them all together and letting the search engine figure out what's the right order to execute and evaluate them and apply changes. This is going to be very heavyweight, more so than the rewrite stuff we'll see today. And then you may end up doing redundant computations over and over again. So they're going to use basically an internal memo table, it's an internal state to keep track of, have I made this transformation before for this query? If yes, don't apply it again. Again, the unified search we'll cover more next week. All right, so I want to talk about the just quick intro to what Starburst is or was, actually is because it's still around. It's not called Starburst anymore. I want to give a 1 slide or 2 slide explanation of what relational calculus is, because that's how they're going to represent the query plans, at least in the rewriting phase in Starburst. So then we'll talk about what the rewrite rules look like, and then we'll talk about how they're going to do plan enumeration. Okay? All right, so most of this should be redundant for a lot of people here. But IBM is building a lot of data systems for a long time. Actually, I'm missing IMS. That would be 1968. So that would be above that. I'm pretty sure that was the first system they built, at least for databases. Right? We called about System R last class. There was another project after System R called RStar. Who here has heard of RStar? It was the distributed version of System R, right? There was a distributed version of Ingress called Muffin, which I think it stands for like multi-user or something. And then I asked Mike one time, I was like, what does it really stand for? He was like, it's Ingress. I'm like, all right. But it doesn't say that in the paper. All right, so System R and RStar, these were all research projects at the database research group at IBM. SQL DS is the first commercial relational data system that IBM put out. Who here has heard of SQL DS? Still around. Nobody, right? So, but that has bits and pieces of System R. And then the big one that they put out was DB2 in 1983. That was used some bits and pieces of System R. A lot of the system was rewritten from scratch. There was another project called Eagle, where they're trying to put a relational database interface on top of IMS, which is not a relational database system, and that apparently failed. IMS is still around, and I think now they support SQL, but in the 80s they tried to grasp SQL on top of it. That didn't work. And then Starburst was the other big project that they were putting together in 1985. And as I said last class, and I'll say it again at the end of this class, this Starburst exists today, just now it's in the Linux, Unix, and Windows version of DB2. Not the mainframe versions, but it's called LUW DB2 or something. Okay. So Starburst was a major project that was being built at IBM Research after RStar. And the big thing that they're trying to target was making the system be extensible. So be able to add new workloads, add new data types, add new operators without having to rewrite everything. And the key part of that is, again, as I said, it's great to add all these new functionalities, but if it's seen as an opaque box or a black box to the query optimizer, you're screwed. It doesn't know what to do with it. We'll see this problem later on in the semester with UDFs, user-defined functions, where most systems now, again, UDF shows up and they're like, I don't know what's inside of that. I can't make any cardinality estimates about a selectivity or even what's going to do because it can't see inside of it. Microsoft has a way to fix that. We have a better version of that. We'll cover that later in the semester. But again, the idea is like, if you want to add these things, you have to tell the optimizer, here's what I'm adding. Here's what it's going to do based on the properties that you care about in your query plan. Right. So this is the same motivation as Postgres, but I don't think Postgres didn't do the integration with the query optimizer in the way that Starburst did. And so I actually found a video of a promo video from 1990 of Starburst. I want to play this. Let me turn this down. It starts with this weird ominous music, and the intro's really long, so it'll fast forward through a bunch of this. The intro's like a minute long. I was like, I can't play this. Yeah.
Information. We accumulate it, analyze it, and store it away. And every year that passes means that much more information to be processed. Access to this explosion of knowledge comes from database systems. Given a query, a database system will sift through vast amounts of raw data in order to find the requested information for the user. But new information may not always fit within the model that today's systems can use.
What we do know about this information explosion is that we need to find ways to make database systems more adaptable.
She's the first author in the paper you guys read.
Data. We need solutions that will work for the needs of tomorrow as well as the needs of today. The Starburst project here at the Almaden Research Center is our answer to this problem.
Starburst is an extensible database system. That is, new types of data and the access methods for retrieving these types can be defined directly in Starburst. For the user, this means that the addition of new types to the database.
That's the guy that ran the query optimization. That's Guy Lohman. All right, well, fast forward to all this, right? It's some example where, like, hey, you want to find all the campsites in Santa Clara, and then you basically introduce a new index type that you didn't have before, and you have to expose that to the query optimizer of how to do it. But you can still write everything in SQL.
We could have defined two different indices into the parks table. An index to all parks having campsites, and a second index to all parks in Santa Clara County. The query optimizer is able to tell that the index to parks with campsites would cause more rows to be examined than the index to parks in Santa Clara County. Therefore, the optimizer chooses to access the data and answer the query using the index to parks in Santa Clara County. How did the optimizer know about the strategy using our new spatial index and what it could do? Starburst specified this information through a powerful set of optimization rules.
Right, so that's going to be
as data to the
rules. Those are the stars.
The rules tell the optimizer what execution strategies are available and what they cost. Starburst's rule-based approach to query optimization is tremendously powerful and flexible.
So these are the stars, and those are the lollipops.
And can be applied to any table. Each rule is invoked by name so the optimizer can quickly determine which rules apply. The optimizer can explain to the user why it chose a certain strategy by simply listing the rules it used to construct that strategy. And best of all, since the rules are input as data to the optimizer, the user can instruct the optimizer to change old strategies or define new ones without having to change the optimizer itself.
We'll cover that in a second. They got rid of that.
Starburst's extensibility allows us to support new applications with new demands for new types of data and new operations. Achieving extensibility is technically challenging because of the need to ensure good performance and data integrity. Rule-based optimization and recovery are just two of the research issues that we are addressing in Starburst.
Well, hold on. So, I can't pause it, but there's some famous people here. Hold on. Are you laughing because it's the 1980s?
Yes.
I don't know why I can't move them. Hold on. All right, hold on. That's Jennifer Whittam. I mean, who she is? She's dean at Stanford, right? And the paper you guys read, we're not doing that. The author, she's the dean of UMass Amherst, in computer science now, right? There's a bunch of other famous people. The guy that invented Aries, he was on that list as well. All right, so I think you brought this up yesterday, but like, oh, it's called Starburst because they're bursting stars.
I mean, yes, they're going through a bunch of stars. And
that's right. I mean, I'm like, all right, seems reasonable, right? But then you didn't know about R star, so I was like, is it what's the meaning of the name? So I emailed the author, and she's the dean at UMass, and she said the name. This is last night that actually. So I didn't ask ChatGPT. I used Perplexity, and it got it right. That basically the name was really meant to be. They were trying to build something based on R star, and they pivoted to this extensibility thing. And the idea was like they blew up the bits and pieces of it, and then that became Starburst, right? What?
In the video, they said that the stars have the cost in them. There is no mention of that in the paper.
We'll get that in a second. Yes, that's in there. All right, so this is the best paper of all the Starburst papers that I picked for you. There's one called "A Star Is Born" or something like that. That you can't find anywhere. It's like it's listed on the IBM website. That's supposed to be the overview of Starburst. I can't find that. Right, but that one, the one I send you guys, is the only one that covers the rewriting and the and the cost-based optimization. So that's why I had you guys read that. There's other ones where they just do rewriting. And then the guy I emailed the one of the other guy co-authors, the guy in the green shirt that was typing, and he sent me his slides this morning. I actually used bits and pieces of it, but he had like a sort of full overview of everything that Starburst is doing in the query optimizer. All right, so here's the pipeline. Right, this is going to start to look more advanced than what we saw in System R and a sort of general overview. Right, we still have a parser and a binder, right? Because we have to do evaluation to make sure that any names or tables actually match to something in the catalog, right? But they're going to take the sort of the logical plan that comes out of this, the parsing and the validation, and they're going to store this in a graph model called the query graph model. And we'll go over what that is in a second. And then now the query graph model, you sort of think of this as like it's a logical representation of the query plan in tuple relational calculus, which we'll cover in a few more slides, right? So this is the logical plan, but then now the binder says, okay, I'm done, tells the query writer to pick it up, sucks in the query graph model, applies a bunch of these rewrite rules that we'll cover, and then can come up with refined versions of the query graph model. And again, the output of this, the first stage is always going to be a valid query plan, a query graph model, and any rewriting you do subsequently will always produce a valid one. Then you hand this off now to the controller, to the plan optimizer, then takes this in, applies additional rewrite rules, these are the stars, to then generate a physical plan. There's additional refinement step, which it doesn't really talk about. We'll see this in the Microsoft one. Sometimes like if you know you need to go distributed, then you start off with a single node plan, and then refinement can then break it apart or do multi-node, right? And this is sort of showing one pass in, but they're actually taking the query graph model and generating a bunch of different alternatives based on the stars and the Lolepops, and then that does the costing to figure out which one's the best one. And then once this is all done, then you have a physical plan that you can actually execute. Okay? So we're going to talk mostly about this and this. The paper doesn't talk about what this is, and we'll have to define what this is as well, and the thing at the top. Okay? All right, so before we get to that, we got to explain what the hell relational calculus is, right? So we made a big deal at the beginning of the semester, and I make a big deal in the intro class about how you always want to be using a declarative language when you query your database, right? Instead of a procedural one. I showed that example of like, here's what codicil looks like according to JetGPT, and then here's what a SQL query is. Look how much better it is, right? You definitely always want to be using a declarative language. However, when we talk about query plans, and we always talk about it in terms of like, oh, here's the SQL query, and look, I've converted it into relational algebra. And then I can take that relational algebra and convert that into a logical query plan. But relational algebra is procedural, right? It's defining the order in which you apply things. Like I am joining table A with table B, right? Depending on what side I'm on that join operator in my relational algebra, that's going to determine the order that things get applied. Likewise, like if I want to do predicate pushdown, I got to move the filter operator to be the inside of my selects. So Starburst, instead of doing representing the query plans as relational algebra, which again determines the order that things occur, they're going to be a little bit higher level or more higher level and represent things in relational calculus. I don't teach relational calculus in the intro class anymore because you don't really need to know it unless you're doing query optimization. Guess what? You're doing query optimization. But it's not that hard, okay? The basic idea is that it's a higher level non-procedural language where the calculus is basically forming tuples based on some predicate. Right? So the basic form of a relational calculus query, this is like the most watered down version, is that you're going to find some tuple T that's going to be come from some predicate P on that T. And that's just like the qualifier to say, like, if a tuple from some input, which I haven't defined, matches this predicate, then I can put it as part of my output of my tuple. So T is just a tuple variable. If you have square brackets, that's how you identify or reference the attributes or columns in a tuple for where it's coming from. And then you say a tuple is in relation R, means that basically it's coming from some source relation. And the P is just going to be a formula similar to what we've seen before, right? It's based on predicate calculus, or like predicate calculus. It's just all the conjunction clause, or clause, all the where clause predicates that we talked about before. There's also domain relational calculus, which is basically the same thing, except instead of defining like, oh, here's a T from a tuple from a relation, and then you explicitly build the tuple by putting the attributes you want in it. In domain relational calculus, you basically define T as being like, here's the attributes that I want explicitly. They're basically the same. It doesn't matter for us. All right, so let's see a query where you, in relational calculus, where you want to get the ID and the salary for all the employees whose salary in some employee's relation is greater than 50,000. So the way you write this relational calculus is basically, here's my tuple T that's going to be part of my output, and you have the exists. So there exists a tuple S in some employee's relation, and I'm then defining the predicate that I care about, or I'm sorry, the attributes that I care about that I want to populate in T. So I say there's some T here, there's an ID attribute, and oh, it comes from S's ID attribute. Likewise, there's a T, there's a salary attribute in tuple T, and it's going to come from the salary attribute. And then we have our conjunction clause to say where salary is greater than 50,000. So for all the tuples S in relation employees, only match the ones where the salary attribute is greater than 50,000. That's it. And then here's the equivalent relational algebra. Is one variation of it. Right. Again, the pointing out here is that I have the projection here and then the filter. I can swap these, like I can do the projection first, then do the filter, and that's still equivalent to this. But in relational calculus, these clauses inside of this, the order doesn't matter, right? Because it's a higher level logic here. It's saying like these things have to be satisfied in order for a tuple to come out of this query. Any questions? Yes.
The backwards E means
Exists. It's essential. Yes. The other one is universal, all upside down A. You do that for like nested queries and joins and things like that. This is it. It's all you need to know for relational calculus for the semester. I'm fairly certain, right? All right, so what can we do with this? Okay. Well, again, if we want a way to represent the query in some abstract form that doesn't define the order that we're going to apply things, right? We could base that on relational calculus and use that as the for our representation. Of course, we don't want to be doing query optimization or rewriting on this, right? Because this is too high level. We need something that has a bit more meat on it that can just describe here's the actual properties of the data we care about, and then allow me to manipulate things accordingly. So this is what they're going to do in their query graph model. So it's going to be an internal representation of a query, and then that they can then do pattern matching on the structure of that graph to then identify when they can do rewriting to move things around, right? You can start to think of the query graph model as like the in-memory database of what's inside the query. So then you can do lookups in that in-memory database and say, do I have this structure or do I see this pattern? If yes, then go ahead and do some change, right? And that harkens back to that active database stuff we talked about at the beginning. So the query graph model is going to describe the input and output of tables and the relationship within a query, and they'll be sort of put together in a box to sort of organize things. And every box is going to represent or contain the body that has all the quantifiers that perform some operation on some inputs. And going back to my relational calculus back here, right? Oops, sorry. The quantifier is basically this, right? There exists a tuple such that it has there exists a tuple T such that there's a tuple S that has these properties that get satisfied. So the body is going to define that piece, and then the head is going to be for all these boxes in our query graph model are going to denote or keep track of the metadata about the output of that query box and the various properties about it. Being all hand wavy doesn't mean anything. So let's actually look at an example here. So this is the query we're going to do: get the suppliers and parts information for which the supplier's price is less than all the other suppliers. So it's a nested query where we have the outer query doing a join on inventory and quotations table, And then we have this nasty nested query with the all predicate that's going to go get the price of the part that they're trying to look up on. So this is basically saying for any part in inventory as part of Q1 for that price, if it's less than all other prices, meaning it's the lowest price, then the predicate would get satisfied. So the query graph model is going to look like this, right? And we'll go through it bit by bit. So the first thing is that we have the stored tables, meaning the tables that are actually in our database, the user-defined tables. These are represented down below, and they're basically just empty boxes. There's the name of the table, and then there's some output columns that come out of it, right? And that's it. But you could add additional properties, like if it was already sorted on a cluster, right? You put that in there as well. Then now you would have these query boxes that correspond to the two queries that are in a query plan. So in the initial form or the initial version of a query graph model for a new query that shows up, every nested query would be treated as its own box, right? And the outer query is obviously treated as the box. So these are the two select statements that we have. And then within that, we have these vertices that represent basically the iterators, right? The things that are doing some operation on a stream of tuples coming in, right? And the two forms of the iterators are the set formers, right? The things that are creating new outputs from from base tables, right? Or it could be a quantifier that is something that's being generated as from being derived from another query box, right? So this select here is doing the scan on the quotations table, so therefore it is a set former. These two guys here are both looking at inventory and quotations, so they're both set formers. But this one here, Q4, is being derived from the output of the second box here, so therefore that's why it's a quantifier. Yes.
Is there a way to think about this that it's more like you can do this pipeline execution as a materialized execution in your actual engine? Because if you have something that's a set former, that has to be materialized. No, that's not necessarily true. You're like way ahead. No, like there's no notion of materialize anything here. It's just saying like here's the logic of how this query wants to operate to produce the correct result, right? I mean, the answer is yes when we convert these into for stars and then get down to lollipops, then you can reason about those properties. Yes, but not here. Yes.
So when it starts execution, so can we say like the first the nested queries get executed, or is it given as a preference?
His question is, can I say anything about the order in which these things are being executed? Not at this level, no. Right? Nothing. Again, there is no notion of order of operations in relational calculus. It's just like if I execute this, I don't know how, but if I do it, then I will produce the correct result as required by the query I was given. That's the way to think about this. Other questions? Okay. Then now they have these qualifiers. Right? These are basically sort of like the predicates. They're represented by these rectangles that sit along the edges between them. And then we have, again, for the output of each box, it's going to say, here's the column, the name of the attribute that's coming out of me. And then below that, you would have like, where did it come from? Right? So this box is producing a single attribute called price. And this is just saying that this price is being derived from whatever Q3 is reading from or generating data from. It'll have a price attribute. You can have like the data type in there as well. The other thing that I don't think is very clear in the paper I assigned you guys, I think they talk about in the head these distinct flags, but they don't talk about what's actually inside the body as well, and that'll come up in a second. But they want to keep track also of, is the output of a box going to be distinct or not? And this has to do, again, of determining when you're allowed to merge boxes together, and are you guaranteeing that the properties of just uniqueness to ensure that the result is going to be correct. So it's sort of easy to understand, like within a box, it's saying like, yes, the output here, is it going to be distinct, yes or no? But then they have this inner part here, right? So the select is saying, here's the operation that I'm actually doing, right? This will be equivalent to like almost like a lollipop, but it's really a star at this level. And then you can also say things like, am I going to enforce whether things are going to be distinct or not, or can I provide a hint to anybody that is reading from me, is my data going to be distinct or not? Because maybe my box is not the one that's going to enforce distinctness, but it's coming from below me because the thing I'm reading from, right? So this is saying distinct equals permit. So that means that you're allowed to, the box is allowed to produce duplicates. They may or may not be, but they're not doing any explicit checking here. Whereas and up above, now we have distinct equals enforce. So that's saying that there will be something we're going to do to guarantee that whatever comes out of this box, no matter what is being fed into it, that for the attributes that are coming, they're finding in our head as our output, those will be distinct. Is that clear? Okay. All right, so if you got this query graph model, what can we actually do with it, right? Well, as I said, the initial query graph that's going to come out for any query is guaranteed to be valid, because there's almost like a literal translation of what was in the SQL query into relational calculus as defined in the query graph model, right? But in order the first version of this, we'll have to split all the nested queries that we have so that every select is going to be in a box by itself, right? But then the challenge is going to be that when we start doing query optimization, the cost-based rules, that the application of the cost-based changes or transformations in the second phase, now if our nested queries are split across a bunch of boxes, now we got to write rules that can look across a bunch of boxes, and that becomes very tricky because you have to try to handle all possible corner cases of the boxes. And the dirty secret, and I'm foreshadowing what we'll talk about later on, but if you take in 721, you know the answer is that nobody, except for the Germans, handle all possible nested queries. Even DB2 doesn't do this. For much as they tout how great they are in this paper, they're not going to do it correctly either. They bash on Oracle in one of them. They're better than Oracle, but they're not as good as Microsoft. But the Microsoft isn't as good as the Germans. We'll cover that later on as well. Because of our paper, they make sure that they match the Germans. And we have a we'll cover that later. Okay. But basically, what I'm trying to say is like they want to get rid of all the nested queries before they get to the plan-based optimization. So in this, what they're going to try to do is now take a query graph model and then find any query graph model that has multiple select boxes, try to merge them together so that you have a single select box. So now you can reason about that box without looking at other boxes. And now, because now you can do all the join order stuff and enumeration and all the other predicate push and all the optimizations we talked about before. Now you can do that within the single box, because they can't do it across multiple boxes. So this is what the rewriter is going to do. And again, under stratified search, there's multiple phases or multiple stages. This is the first stage you're going to hit after generating the query graph model to do apply heuristics and rules to rewrite the query graph model into another query graph model that is more amenable to the cost-based optimization or the dynamic programming stuff that we're going to see later on. And as I said, the idea is that if a query comes along with a bunch of like nested subqueries inside them, you want to be able to collapse that down, because if since the cost-based the cost-based search optimizer or that search algorithm is not going to be able to reason across multiple boxes, it will end up basically producing it's almost like implicitly defining the order in which operators have to get applied if you don't do this unnesting. So that's their big goal, is that they want to be able to rewrite it to get it in a form that is going to be better for the cost-based search. And it's basically by applying transformations that we know is always going to be a good idea without ever referring to a cost model. Because that's an expensive lookup to go derive some cost estimate, but what you think the query plan is going to be, or what the query is going to do. All right, so this is cool. This seems like a good idea. So what do these rules actually look like? So there are going to be high-level specifications of what are valid or legal query graph model representations or alternatives for any one query graph model. So each rule is going to be defined in terms of the matching condition, like what has to be satisfied as true in my query graph model for then me to apply some action function that then goes ahead and makes the change. So they make a big deal. It's not clear in some of the bunch of papers. They talk about, oh, it's a high level declarative language, but then in other papers they say, oh, it's in C. Then later on they say, oh, it's in C++, right? And then in the Volcano, or certainly in Cascades later on, they're going to make a big deal about having a DSL where you can define these rules and not something that isn't C or C++. But that doesn't always work out either, because sometimes you really do need to have low-level access to the query plan to make changes. Right? Cockroach does the same thing. They try to define a DSL when they can fall back to Go if they need to. Okay, we'll worry about that later. But just know, at least in the initial version of this, as far as I can tell, everything's in C, right? And then one of the cool things they can do is that they'll keep track of all the rewrite rules that they apply during this rewrite phase. And so then when you're like say the database developer, or even the end user, when you want to go look at why did my database system generate this query plan, you could go back and look at, here's all the rules that applied to get me to the rewritten form here. Now, is that entirely useful for an end user or an application developer? Probably not, right? Because it's going to be a bunch of these rule names that we'll see in a second. Like, they're not going to know what any of those things mean. But it's certainly be useful for the person building the query optimizer to understand, or has to debug it, why the query optimizer made certain choices. Because then it's less of a mystery. So they're going to have rules for doing manipulations. They'll have the ability to apply rules inside of rules. They can also control the order in which rules get applied. So you think of, like, if I know that some rule is usually doesn't matter, it's going to make a big difference, maybe I'll give that a lower priority than a rule that, like predicate push down, where you're always going to want to do, or unnesting, where you're always going to want to do those things. Right? We'll see this again in Cascades. They have a notion of ordering priorities as well. And then they have to be able to guarantee that the rules will eventually terminate. Right? We'll talk about how they handle that later on. It's basically they set it like you need to go about, like, what's the wall clock? How long have I been rewriting? In other times, you say, if I apply 100 transformation rules, then I go ahead and once I do 100, then I'm done. All right. So then they also have this rule. They have to have this rule engine as well. And again, the idea is that you can control how the rules are applied. Are they done in sequential order? Or the priorities? They talk about how you can have the ability to provide a probability distribution, so that when you flip a coin, what's the likelihood that one sort of category, a class of rules, will get applied versus another. I don't see that being feasible for anybody. But at least they expose these things. And again, as I said, you're given some budget. The system is given some budget for how long they're allowed to search, or how many transformations or rules they're allowed to consider or apply. And then when that's done, the processing just stops. And because we have this guarantee that any transformation that a rule does in the rewrite phase, the input is a valid query graph model, and the output has to be a valid query graph model. That means we can terminate at any moment of the rewriting phase, and we'll be guaranteed to have a query graph model that we actually could then convert and run it in its entirety. Right? We're not going to be able to do that in Cascades, because if you terminate early without actually getting down to all the leaves of the search tree, the query is not fully formed, right? And again, slightly different problem, because they're just doing heuristic rule writing. But that's important thing to understand here. Like, they can shut this thing off anytime when the query shows up, and everything works okay. So rather than showing again how they manipulate the query graph model, I'm just going to do it in terms of SQL. But say we have a select query here that is accessing some view that we define. So you can define a view to do some lookup like this, and then you have a query that's going to do a join against that view as if it was a real table. The naive thing is basically to take wherever you see the view being accessed, treat that as like a macro where you just fill in whatever the view definition actually was. So now we're kind of stuck with this nested query here, and we want to figure out how can we want to apply a rule that can then allow us to merge the query box of the outer query select and the inner query select. So this is an example of what the rule would actually look like in basically pseudocode. But it basically says, if I'm in a select box, right? So as I'm traversing the graph model, then if I would define whatever select box I'm in is the upper one, and it has a quantifier that is doing a set former, meaning it's reading against a base table, and I'm doing a range over the inner query that the table I'm referencing in my lower box is also doing is also a select, and they're doing a there's no other select boxes accessing the lower box. I think I have two boxes. There's one edge going into the lower box. Then I have a bunch of these additional checks here based on those properties I talked about before. Where like, if my output needs to be distinct, and or I can allow things not to be distinct, or the other guy down below me is not going to enforce it that are distinct. If either one of these are satisfied, then I know it's okay for me to then merge the two select boxes so that the inner query is then accessed together in the same level, in the same query box as the first query here. But then there's some additional logic here. So this is the action that gets applied. And you do the merge, and merging two boxes, but then you have to clean up these properties to know that, like, okay, well, if the lower guy was telling me that they were enforcing things to be distinct, and I'm not checking that, then I'll make sure that I'm enforcing that things are distinct, so that my output ends up being distinct, right? I should have shown the rewritten query, but you basically end up with a query where it's a join instead of a nested query here. So this is pretty gnarly, right? This is a lot of logic you got to figure out. Like, okay, if something's reading something and they're distinct or not distinct, and are they accessing things in terms of directly from a derived table or a stored table, right? Like, this is the easiest example I could sort of come up with from the papers, but like, it obviously gets way more complex. And so this brings up also the question of like, okay, well, how feasible it is to think that like someone's going to be able to extend the query optimizer that isn't an employee at IBM or whoever is building the database system. Right? Postgres doesn't allow you to do these things. They have rewrite rules, but they're really to just inject views into the query. They don't try to do any additional manipulation to optimize it further. All right, so this is roughly what these rewrite rules are going to look like, which are going to be different than the rules we'll see for the stars and the glue and the lollipops when we actually do the call-space optimization. So again, the idea is that we will start with the initial query graph model. We'll do the rule engine will see which one of these matches. When they do a match, then you apply the change, and then you just go back again and check. See, now in my new query graph model that since I've modified it from this rule here, is there any other rules I need to apply? And you keep doing that over and over again until you either run out of time or there's no more rules to apply. Okay, so then now we end up, now that we finish the rewriting phase, now we have a query graph model that is valid. Now we actually have to convert that to something we can execute in our database system. Again, the query graph model doesn't say anything about the order in which things are going to be applied. Right? It's a logical plan. It doesn't tell you what join algorithm to use, what indexes you're going to use, what tables you're going to use. Right? We got to figure that out now. So now they're going to do more rules where they're going to transform the high-level constructs that are, or operations that are in our query graph model, which they call the non-terminal operations, like the high-level ones, and we're going to convert that into the terminal constructs, the lollipops, that define how you're actually going to be able to then execute the query plan. And what's interesting about these rules is that unlike in like, if you're parsing a grammar file, like trying to parse SQL, where you're really trying to, for a given SQL string, you're trying to find, here's the exact unique tokens that are within my SQL string. In this world, a rule may actually produce multiple outputs because there's multiple alternatives you could choose. Like I have something that says access this table. Well, I could have a bunch of different access methods, like based on indexes or sequential scans or whatever, that will emanate from applying that rule to say, here's the different choices that I can apply. So rather than like in System R, where they're basically saying like, all right, give me all the possible tables I could have for my join order, and then for each one, I'm just going to iteratively say, here's the possible join order, join method and join order I could have. It's all going to be based on these rules, so that it's sort of guiding the search in a more intelligent way to say, here's the possibilities that that are valid for me beyond just the join order. So the grammar file, again, it's going to basically very similar to what we saw before, where you have these conditionals that you want to check to see whether they get satisfied, and if they do, then you go ahead and apply the change. And again, the idea is that the query graph model can be translated into the stars, the high-level concepts, and then we want to convert those stars into the other stars, which then can get converted into other stars and so forth recursively. Or eventually we'll end up with a star that then converts into a lollipop. And once our query plan is entirely comprised of lollipops, then that's something we can actually execute or interpret in our engine. Right? All right, so what is a lollipop? Lollipop is just a database operator that we actually can execute. It's an extension of relational algebra that includes additional functionality that isn't defined in the initial relational algebra, or at least the original relational algebra, but you actually need it to actually run something, right? In relational algebra, at least the initial definition of it did include a sort operator. But obviously we need sort, we care about that. The relational algebra didn't have a sort of operator to do accessing tables from some location, right? I guess you could say the select operator is sort of that, but it didn't have an explicit operation to store something into an operator, or sorry, into a table. So the access basically converted the stored tables into streams, and then the store is converting the streams into stored tables. And the ship is basically like to send things over the network if you're doing a distributed system. So each lollipop is going to take one or more tables as inputs and always produce a single table as its output. So that is an interesting limitation, right? Because in some cases, and we won't go too much in this semester, but like in some systems, you actually want to have one operator generate multiple outputs. Like if you know that it's some subquery or some portion of the query plan is going to be used by other parts of the query, you may want to have an operator produce multiple streams coming out of it. And so they can't handle that. So the lollipop would be something high level, or not high level, like I want to do a join, I want to do a sort, I want to do a ship. And then rather than having different physical operators that represent the different implementations of how you do, a join, for example, you wouldn't have a hash join lollipop or sort merge join lollipop. You have a single join lollipop, and then the input parameter into that lollipop specifies what the, as they say, flavor of that lollipop is. So you would have an input parameter to a join lollipop say, I'm going to do a hash join, or I'm going to do a sort merge join. And that's different than what we'll see in Cascades, where they'll have explicit operators for the different join implementations and so forth. All right. In the case of System R, System R just kept here's the sequence of operators I actually want to do on these tables, and then the things you actually did on them was sort of implicit as part of that. Meaning again, you would say the operator would be do a hash join, and then you would scan some table, do a hash join with another table. You would sort of define explicitly, here's the steps I want to do. These lollipops are still a little bit more high level than that. All right, so then you have these things called stars, where again, these are just going to be the declarations of the high level operation that I actually want to do. And then it's going to have a bunch of rules that allows us to rewrite stars into other stars or stars into lollipops, so that we end up eventually converging on a query plan, again, comprised entirely of lollipops. And so they make a big deal about how a star is just a named object. We saw that in the video where they were like, oh, here's the table scan, and there was sort of this this bracket and a bunch of these so alternatives below that. Those were the stars. You're saying the table access is the star, and then I can rewrite that into either a B tree lookup, R tree lookup, or special scan lollipop. And the idea, again, we're defining how we build these high-level constructs from these primitive operations, rather than going from a high-level operation and explicitly then converting it like a logical operator and explicitly converting it to a physical operator, which is what we'll see again in Cascades and Volcano next week. The other thing that they're going to do that System R didn't do is now have a notion of explicit properties in a query plan. We kind of already saw this in the query graph model, where they're like, oh, they're keeping track of whether things are distinct or not. But now in our query plan, we're going to keep track of things like what's the cardinality of a predicate, or a filter operation, Like you can actually keep track of those things in the query plan itself. It's being derived from the query optimizer cost model because it has to look at the statistics and guess what the estimates are going to be. But all of that now is going to be embedded directly inside the query plan. Right? Remember, from System R, they had this notion of interesting sorts or interesting orders. And that was like a thing on the side that they would keep track of, like, okay, well, yeah, I guess I kind of need to care about the sort order, but it wasn't embedded in the query plan. It was sort of like on the side auxiliary thing. But now we're introducing properties as first-class entities in our query plan, so that if we're trying to start reasoning about what transformations we can make, if we know that a query plan, transformation would affect the sort order property in a certain way, then we have to then go ahead and patch that up. So what they're going to do in Starburst is they're going to have these things called glues, where it's basically they're special stars they add in to make sure, like, hey, this thing doesn't look like the way I expect it to look like. Go ahead and change the query plan to introduce a lollipop that will guarantee a property that I care about. So again, it's sort of like System R patching things up, but they're doing this in, again, a more systematic way rather than, again, a hack near the end. And again, I keep bringing up cascades, but in cascades, it's going to be different. We're going to have these enforcer rules that say, you can't do this transformation if it violates the property that I care about. So they're kind of almost there, but they have the glues to go ahead and fix this up, right? So this is what I just said. So these are special stars. They keep track of the cheapest plan satisfying the required properties for a query. Basically, it's a formal definition of what System R was doing. But then they go back and see, okay, well, if my property requirements are not being met as defined in the glue stars, then I can go ahead and the glue star will get rewritten into a lollipop that then does the sort or whatever it is that actually would need. Or if the property is there are no properties, or the property that I care about is actually being satisfied, then the glue just gets rewritten to a no-op and discarded. Actually, going back here, the other important thing that's going to be different than in Cascades of Volcano is that the execution cost of a query plan or an operator within the plan tree is actually embedded as a property as well. I'm not saying this is good or bad. I'm saying this is going to be different than what Volcano is going to do or Cascades is going to do. Cascades is going to have the cost as being on this thing on the side. Like, what's the cost of the best query plan I've ever seen? But it's not embedded inside of the query plan itself. They're going to keep track of these things in the memo table. And there'll be pros and cons for both of these. But that's another big distinction here, is that execution cost is just another property. So if you now want to say, what's the cumulative cost of this query plan? Well, as you're converting the stars and the lollipops, and they're each going to have their own cost, you can then just sum up what those costs going from one operator to the next. Doesn't always work right, and there's a lot of assumptions that they're going to make, which we talked about before, where these calculations get way off. But we'll cover that in a few weeks when we talk about cost estimates. All right, so I was going to put together an example of what these, how to apply these stars. Then the guy, again, the guy named Guy, who worked on and helped build the Starburst query optimizer, he sent me his slides this morning from a talk he gave at Microsoft last week. I mean, the fonts are all funky, but that's okay. The material is what matters. So this is his example of what the transformation process looks like, or the query optimization process looked like of rewriting the stars into glue in DB2. And this is derived from this paper he wrote from 1988. All right, so again, the rules can specify a bunch of alternatives, like a grammar, and each alternative can specify a nesting of other rules or lollipops. So you would start at the very high level. So the green is going to be the rule names, which again are going to be the stars, right? And you would say, okay, I have an access root on table T, and I can either rewrite that into a scan lollipop, or I rewrite that into another star that knows how to access that table, but against some index, right? And then this can get exploded further. Say, okay, well, here's all the different ways I can access indexes, right? Do I do a bunch of access multiple indexes and the results together, or them together, right? The different versions of these things. This is all DB2 specific, but each of these stars can then get converted into the lollipops that would be used and then execute their corresponding operations, right? And then, so then these can then all be converted now down into the, either I have explicit indexes that I would need, or I can go ahead and actually go ahead and create the index that I want. So this idea here is like, say for this one here, what's an easy one? I do a fetch from some tuples as I'm scanning it, but then the star of reg index scan gets rewritten into a lollipop called fetch, and then another star called index scan. Then I got to then apply a rule that rewrites that to actually then do the index scan on the explicit index that I want. They do the same thing for join order. I'm not going to go through all the animations here, but like again, at the very top, you say I'm going to join two relations, or like table S and table L, right? Based on some quantifiers, and then I can then apply rules that can switch the join order, right? I can then have different choices of how I'm going to then do the join. Then it get exploded by applying the rules to rewrite, again, this join choices star into a nested loop join, merge join, or a hash join. And each of those then get recursively, rules recursively applied on them to then convert down to how you're actually then going to physically execute the query plan. So again, the rules are just defining if I see this pattern in my query plan tree, either based on a star, then I can go ahead and rewrite that into either a star or set of stars and some lollipops. There's not going to be rules to do from lollipop to lollipop. I don't think there is. So this note here he wrote, this is basically what I was saying in the beginning, where like in that video they showed, oh, all the rules are entered into the database just as data, and then like an active database, and then you're checking within the database itself, do any of my query plans match the rules that are specified in the database? They got rid of that, and then when they actually put this in production, they're basically now compiling the rules. So I don't know again whether it's a DSL or one of the papers says it's in C++. I think it's in C++. So these rules they find in procedural code that then get compiled, and then there's some rule engine that can quickly apply them and see whether you have any matches to generate the rewrite quickly. Okay. All right, so how long does this go, right? Well, as you said before, you can just look at say how long am I running in the wall clock time, right? In Postgres, this is basically how it works. Postgres, you can set a timeout for how long the query optimizer is about to run, and then once it's done, then it does the final cleanup and refinement, and you're given whatever the best query plan that it had. You say a cost threshold. So if as I'm doing my transformations, I'm going to keep track of the best query plan I've seen before, and if I somehow know what my the upper bound is, or what I care about, if I'm within 10% of that, or if I have a query plan that I haven't seen any improvement in the last 1,000 iterations of or transformations that I applied, then just take whatever the last one is, because I'm unlikely to find a newer one. Most systems don't. No, I don't think any system actually does that in the real world, but some papers on it. That one could be like if you know that you've gotten all the possible, you've looked at possibly everything, then you just stop. Like if it's two tables in your join, if you're joining two tables in your query, you can explore those two choices pretty quickly. And then the last one is what DB2 does, or Starburst does, and what Microsoft does, where you just say, I'm going to apply a certain number of transformations, and once I reach that limit, no matter how long it actually takes, then I just stop. And we'll cover this more next week, but the Microsoft guys, what they talk about is, which I never thought about, which makes sense, is that the reason why you want to do this one is because no matter what the load of the system actually is, you'll be guaranteed at least that the query will always be able to produce find what would be the best query plan, whether the system was loaded or unloaded. Meaning, like, if the system is completely idle, and I'm going to do 1,000 rule transformations, then I'll find some query plan. But if the system is taxed, or thrashing disk is very slow, then although it may take me 10 times as longer to generate that query plan, it'll still be the same query plan as when I was underloaded. Yes.
Wouldn't that also still be true with like the, I guess, ready and descent method of number 3, where you just keep going until there's not much
Yeah, so what statement is, and he's correct, yes. If you're doing gradient descent with this, you know what he does, then you basically say, yeah, once I level out, then I stop. Yes. But nobody does it. There was a research paper we're not going to cover on doing like simulated annealing. There's some systems that can do like try to use like neural nets to try to find better query plans, but nobody finished this one. Either you do the first one or this one, and the commercial guys do this one because it's better. MySQL, they try to sort of related. MySQL will do like how deep you actually want to go in the query plan. So you can say like how much you want to actually explore. We say, okay, I've done enough. So you can go all the way down. You go some part down, but again, we're not going to talk about that. Okay, let's finish up. So as far as I know, Starburst was one of the first query optimizers that represented query plans in this higher level form in tuple relational calculus, and then to allow them to be able to have rewrite rules that can just operate on what the query wants to do rather than the operation ordering within the query itself. Like before you get into a query plan that specifies I'm going to do this followed by this followed by this, you want to operate on something that's higher level so that you can move things and manipulate things no matter maybe the exact form of certain things. There's a lot of other interesting aspects of Starburst and DB2 optimized that we'll discuss later. We'll see methods how they can take feedback from what query actually runs and observe that their cost model estimates are way off and try to use the behavior they see to update their statistics. Again, there'll be paper we read about these links later on as well. And as I said at the end of last class, there's this great blog article written by the data center god at Amazon, James Hamilton, because he used to work on DB2. And this blog article, they talk about how the Starburst system we've been talking about in that video you saw as well, like that was just a research prototype when IBM tried to build a version of DB2 that run on OS2, like their operating system. The performance was terrible. And then the IBM research team got the Toronto team that was building that version of DB2, got them to actually use Starburst. And Starburst exists today in the Linux and Unix Windows version of DB2. And James Hamilton was part of that team that ported that. Okay, so that's it for today. Next class, now we're going to talk about these unified query optimizers. So again, Starburst was a stratified one. We'll talk about Exodus, which is the very first query optimizer generator that Kurtz Graffi built. Volcano is the one that's more important though, and that's what calcites would be mostly based upon. So we'll talk about how these early generators work, and then that'll lead us into the Cascades work later on, which is in the textbook as the second chapter. And we'll cover that on Wednesday.
Little glazed brown. Matter of fact, hold the fuck. This is that wood grain type of shit. Shout out to Blockhouse, my dogs. Get one, Big Al, Mike Stroke, Drumley, all Dynamites. I'm not the one who be amping up the weak ass rhymes. If you spit, if it don't rip through your mind with a sweet anticipated, orchestrated punchline like a reverse the hands of time. Get you captivated quick with the bullshit. I keep the Cadillac equipped for the long trip. I got the remedy for bitches when they start shit. Surround sound like I make them hoes fuck quick and suck dick. Crown me as the thug from the gun. Shit, some niggas claiming that the rapping is sudden. Don't push the button, yes you motherfuckers in front and you don't want nothing. If it did, it'll big star something.